going to talk about doubling and halving time of exponential models. Certainly doubling time has been in the news a lot recently. You know, you hear in the news the doubling time of infections. I know in New York City, last week or so, they talked about the doubling time being 3 days, meaning it takes 3 days for the number of people infected to double, right? Or maybe the doubling time is 10 days. So in 10 days, the number of people infected will double. That's doubling time. So if we're talking about, infection rate at I, then we'd start with our initial number of people infected, and we're saying it's doubling. If we're saying it's doubling every 3 days, we'd write the equation like that, right? Where x is the number of days. That's your starting population. And this is your population after x days. I can even call that I of x, if you will. So you're multiplying your starting population times 2, times 2, times 2 every third day. So here's the question. If I have this model, if we say a population is doubling every third day, what is the percent growth each day? What is the percent growth each day? Pause the video, maybe grab a calculator, and think about how you could figure out if a population is doubling every third day. By what percent is it growing each day? All right, let's grab our calculator. I wonder if you folks took this part right here and realized you could rewrite that as 2 to the 1/3 raised to the x. Does that make sense? So I could rewrite this if I wanted to as my starting population times 2 to the 1/3 to the x. Remember, when you're raising an exponent to an exponent, you multiply? Well, 2 to the 1/3, if you throw that in your calculator, becomes 1.2599 or so raised to the x. Okay. That 1 is your 100%, so every day you have 100% plus, it looks like about a 26% daily increase, okay? So in other words, I could write this same model right here like this, right? They're equivalent functions. This tells me my doubling time is 3 days. This tells me my percent increase each day. So what if I want to go the other direction? Say I have some bacteria, population of bacteria that are growing exponentially. And let's say I start with, 10 bacteria, and let's say they're growing by 3% each day. So again, we'll let x be the number of days. So I've got bacteria, I started with 10, they're growing at a rate of 3% each day. If I asked, what is the doubling time? What is the doubling time? Pause the video and see if you can figure out a way to figure this out. And there are various ways to do it. Okay, well, one way to do it, of course, is just to say, okay, well, I started with 10. I want to see how long it takes to double. Well, double 10 is 20. So I want my ending population to be 20. And so you set up an exponential equation to solve. All right, that's going to work. Let's divide by 10, blah, blah, blah. I have 1.03 to the x. Okay, now 2 different ways to solve this. I think many of you solve this by just rewriting it. We'll call that method 1. just rewrite this in log form. So that's log base 1.03 of 2 equals x, right? And you can put that in your calculator. And you are going to get, drum roll please, x is about 23.44450, let's say. I said method 1. The other method to solve this using logs is one that I like, and that is I just take the log of both sides. I'm going to take the log of both sides, which is using one of those properties of logs. If a equals b, then the log of a equals the log of b. I'm then going to use another property of logs that says if I have the log of a number raised to an exponent, that's the same as multiplying that exponent times the log. And now I just do some algebra. I divide both sides by the log of 1.03. And this gives you that same answer. My doubling time, about 23 days. Or I can say, about 23 and a half days if I want to be a little more specific. Okay, so I just found the doubling time. I just doubled my starting population, and then I solved my exponential function using one of these two methods. Hey, just a little side note for those of you who remember the change of base formula. Hey, log of 2 over the log of 1.03. Log of 2 over the log of 1.03. How cool is that? Let's try another one. What if I said that I have bacteria again, but I don't know the starting population, and let's say the bacteria is growing by 15% each day. Okay, we'll just stick with days. Pause the video, see if you can, again, find the doubling time. Find the doubling time. How long would it take for this bacteria population to double? Okay, so, here's the question. Does it matter what my starting population is? Does it matter? I don't think it does. Just let's pick any number. Let's say I start with 3 bacteria at time 0. Then double 3 would be 6. Well, what would my first step be? If I were solving this, well, my first step would be to get rid of the 3 and then solve that. Well, what if instead I wanted to start with 1,000 bacteria? And I said I started with 1,000 bacteria. Well, double 1,000 would be 2,000. And if I divided by 1,000, oh my gosh, I'd end up at the same place. So the bottom line, and this makes sense if you think about it, when you're looking for doubling time, the starting population is absolutely not relevant. Yeah, the starting population is not relevant because it's going to take the same amount of time for 3 bacteria to double as it takes 1,000 to double, or 1,000,000 to double, or for 1 bacterium to double. All right, that was kind of cool. And then you can solve, again, this using any method. I'll use the method that you folks often use. Log base 1.15 of 2. And that is going to be, drum roll please, approximately about 5 days. So the doubling time is about 5 days when my growth rate is 15% per day. Let's do one of these. Let's pretend that we have a population at time x. My starting population we'll call p sub 0. Let's say that we have a 10% decay in the population each day, okay? And we'll say that x is my number of days, p is my y. So that means if I'm setting up this function, my ratio here would be 0.9, since if I'm losing 10% each day, that means I'm left with 90% of my population. Okay, as we discussed with the doubling time, it doesn't matter what I call my initial population. I'm just going to call it 1. Let's say we start with 1 member of our population. I'm wanting to see how long it takes to halve. So now I'm going to have a 1/2 over here instead of a 2. And then I can solve this using either method. I'm going to use my fun method, where I take the log of both sides, and you can see I'm taking the common log of both sides. You can use any log you like. Property of logs allows me to bring that exponent down. Remember, logs are exponents. So when you're raising an exponent to an exponent, you multiply them together. And then your last step here is just to do a little algebra. Do a little algebra. Da 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 da. And calculator time. We have the log base 10 of 1/2. Let's see, log base 10 of 1/2 divided by the log base 10 of 0.9. And that gives me about 7 days. About 7 days. Okay, is my halving time. Okay, fantastic. By the way, if you don't like this method for solving logs, of course, from here, you can just rewrite it in log form, log base 0.9 of 1/2 equals x. And if you have one of those fancy calculators, it would give you the same answer. Okay, doke. That's doubling time and halving time.